Okay, so this is the last couple of pages of the 7.5 notes. So finally, we're almost done. 10 videos in, 13 pages of notes through, which are just going to be looking at applications of independent events and practicing those cases. All right, so which are independent events is understanding them sort of a little bit abstract and hard, but once we know how independent events work, solving the applications are actually not too bad. All right, usually students can solve those. You just have to remember what it means. Alright, so the first couple of examples, again, is reminding you the difference between independent and mutually exclusive, which is important that you know because they are very different. And so the first two examples here are just formula cases, getting you to understand, using the formulas, what the difference is between independent events and mutually exclusive. Alright, so the first example, we want to find the probability of E or F, right? So the probability of E or F, right, the union. If I use the union formula, it's the probability of E plus the probability of F minus the probability of E and F. Which, I know the probability of E is 0.5, I know the probability of F is 0.4. Well, what's the and statement? I wasn't given the and statement. What I was given is that my two events are independent. The independence will help me find the and statement. Remember, when my events are independent, by definition of independent events, this means the probability of my two events, E and F occurring, is just the probability of my first event times the probability of my second event, right? Independence means I don't have to worry about conditions. So event E happening first didn't change the fact that event F, the probability that event F was going to occur. And so I can find the and statement by multiplying. Right? So I can multiply that out and find out what that is. So that's going to be my first step. I'm going to find my and statement, then I'm going to plug them in here and find... actually, I can plug them in here all at once. I can just write my multiplication there. So that's what I'm going to do. So I'm going to do this. Probability of E plus the probability of F minus, I'm going to find the probability of E and F by taking the probability of E and multiplying it by the probability of F. Right? Because I can do that because they're independent. Alright, probability of E is 1/2. Probability of F is 0.4. Subtract, multiplying those two out to get to the and statement. So I'm going to have, and I said 0.4, but I wrote 0.5, right? 0.4. Now the and statement. So subtract the and statement. Since they're independent, I find the and statement by multiplying the probability of E times the probability of F. And so to simplify that, that simplifies to 0.9. 0.5 times 0.4 is 0.2. And so 0.9, so 0.9 minus 0.2, so the probability of E or F is 0.7, 70% chance of being an E or F. Given their independent events. Alright, so given their independent events, and I know the probability of each of my independent events, I can solve this because the independent events allows me to find the and statement through multiplication. Same setup in the next question, but I'm going to change one thing, but that one thing is going to make a big change. So what I'm changing is this word. I'm switching out independent for mutually exclusive. That's it. That's the only thing I changed, but it does change the final answer. All right. I'm asking you for the or statement. So I want to know the probability of E or F. Well, probability of E plus the probability of F minus the probability of E and F. And it's the E, because I know the probability of E, that's 0.5. I know the probability of F is 0.4. They didn't tell me the and statement. What they told me was the mutually exclusive, but the mutually exclusive tells me something important about the and statement. Mutually exclusive tells me the probability of E and F happening at the same time is impossible, and so that's 0. And so what that tells me is this doesn't matter. It zeroes away. I subtract nothing because there is no overlap. I don't have to worry about any overlap. Mutually exclusive events allow me to just straight out add my two outcomes to find my or statement. And so it's just the probability of E, which is 0.5, plus the probability of F, which is 0.4. I don't subtract anything because they're mutually exclusive. There's nothing to subtract. And so the probability of E or F is 0.9. So again, it mattered. My two events, if they were mutually exclusive, the chance of one or the other happening is 0.9. If they're independent, that means there is overlap, and I can find it. I have overlap of 0.2, and so that time, when they were independent events, the probability was So that's a 20% difference, right? One's 70% and one's 90%, and so that makes a very big difference. So it really mattered the difference between mutually exclusive and independent, right? And so these are sort of giving it to you in the format, right? Mutually exclusive and independent. All right, now we're just going to look at applications. So in all of these applications, they're going to give us a very important phrase. They're going to tell you don't have to test for independence. They're going to tell you they're independent. All right, so halftime at a basketball game, there's a free throw shooting contest. We have three contestants. Will be given the opportunity to attempt a free throw. Suppose the probability of the first contestant successful. So usually when you do these sort of contests, you get to practice. And so suppose based on their practice numbers, they did statistics on their practicing. And so the first guy had about a 0.6% chance of making the shot, the free throw. The second guy only had a 0.25% chance. And the third guy wasn't very good at shooting free throws. They only have a 0.1% chance. 0.1 chance, 10% chance. Assume these events are independent, and they should be assumed they're independent. What one person does really shouldn't affect what the other person does, right? One person's odds of making a free throw is different, separate, than somebody else's odds of making a free throw. All right, and so as soon as you see that, we can assume the events are independent. So I don't have to worry about setting up a tree. I don't have to worry about anything conditional. When I have the and statement, I multiply. When I have the or statement, I add. And then again, I have to subtract if there's an and involved. So, independent events. We like it when they're independent. It allows us to do straight multiplication, and I don't have to worry about any conditionals. So the first one, what's the probability that all the contestants are successful? So probability, the first guy succeeds, and the second guy is successful, and the third guy is successful. Alright, so probability, what's the based on their statistical numbers that was collected when they were practicing or whatever, what's the chance that all three of them make the free throw, right? Make the free throw. What's the chance all three guys are successful? Well, since they're independent, it's just a straight product of each individual probability. So it's just the probability this guy's successful, which is 0.6, times the probability the second guy is successful, which is 0.25, times the probability the third guy is successful, which is 0.1. And again, this works because they're independent events. Right? So only do this when it says they're independent or we've tested and we know they're independent. And so you take your 0.6 times your 0.25 times your 0.1, and there is a very small percentage. So the probability is 0.015, so about 1.5% chance that all three of them are going to make it based on the statistical numbers. Again, this would be an estimated probability based on statistics, so it'd just be a good guess. Alright, the next example is the exact opposite. This is actually the complement to that event, and that's how I'm actually going to solve it. What's the probability none of them are successful? This isn't the complement. The complement's in a second. What's the probability none of them are successful? Let me set it up and then solve it. Alright, so none of them are successful, meaning they all fail. I'm going to use that term. They all miss the shot. Alright, so probability, the first guy fails. He doesn't make the shot. The second guy fails. And the third guy fails. Alright, it is a complement, but it's individual complements. Alright, so this would be, right, not successful. It's an and statement, and they're independent events. And so all I need to know, well, what's the probability the first guy fails? Multiply it times the probability the second guy fails. Multiply it times the probability the third guy fails. Well, these are complementary events. This is the opposite of being successful. And so if the first guy is successful 0.6, right, 60% of the time, he's going to fail the rest of the time. So the rest of the time, remember, all my probabilities should up to 1. And so I would take 0.6, subtract it from 1, and so he's going to fail 40% of the time. 0.4 is the probability he's not going to make the free throw. So it's the complementary of each individual event, right? It's the complementary of being the first guy's success, 0.6. The first guy is not successful, then 0.4. And we can multiply when the and statement's used because they're independent. And so then I do the same thing for the second guy. The second guy is failing, right? So the probability the second guy fails, well, he's successful 0.25, right? 25% of the time. So he's going to fail 1 minus 0.25, so 0.75. 75% of the time, he's not going to make his free throw. All right, and then now the third guy, so we multiply because it's the and statement and they're independent. All right, so since the and is being used and we know they're independent, we just multiply, and then we figure out, well, what's the probability the third person does not make the free throw? What's the complement that he does? So the third person will complete it 0.1, 10% of the time, which means he won't complete it 0.9, right? 90% of the time. We take our 0.1, subtract away 1, and we get 9.9. Alright, so that's the probability all three of them miss the free throw. The first guy misses, and the second guy misses, and the third guy misses. Which, if you multiply that out, it comes out still not a great probability. 27% chance, right? 0.27. So there's a 27%, the odds, based on their stats, 27% chance all three of them will come out and miss the free throw based on their statistics. Alright, the next example. There's that at least phrase again. Alright, what's the probability at least one of the contestants is successful? Alright, so probability at least one succeeds. Well, that means the first guy could succeed, or the second guy, or the third, or two of them could succeed, or all three of them could succeed. So the easier way to solve this one is to use the big complement. Right, I'm going to use the complement in this case, which would be 1 minus the outcome I don't want. Well, what's the outcome I don't want? I want the opposite of at least one person making the free throw. Well, the event I don't want is the previous case. They all miss the free throw. So subtract the case where they all fail to succeed. Right, they all miss it, which is this event. Right, none of the contestants are successful. That's the case we want to throw away. And so we take 1 minus the probability that they all fail, which was our 0.27. So 1 minus 0.27 comes out 0.73. So there's a 73% chance somebody's going to make the free throw. Now, the odds are probably that's going to be the first guy. But based on the statistics, there's a 73% chance at least somebody will shoot and make the basket. Alright, the last one for this set, this probability application. Alright, so E. What's the probability the first contestant succeed and the other two are not? So this is probably the one that's most likely, right? What's the probability the first guy will make it and the second guy misses and the third guy misses? Right? So again, and I can multiply because they're independent events. So probability the first guy is successful times the probability the second guy is not times the probability the third guy is not. Alright, so the first guy was successful 60% of the time. So 0.6. The second guy is not successful, which I believe I have that up here, I don't have to go so far, is 0.75. Alright, he's going to fail 75% of the time, and the third guy fails 90%, 0.9. Alright, so this is probably the event that's the most likely, right? The first guy makes the free throw, the second guy misses the free throw, and the third guy misses the free throw, based on the odds. Alright, multiply that out. Alright, so there's about a 40.5% chance that that event will happen. First guy makes it, the other two miss it. Alright, so that's the probability of that outcome. Alright, so the next example. next application. So Molly enters 2 different sweepstakes contests. Having problems reading today. Probability of winning the first contest is 0.1, so 10% chance. Probability of winning the second contest is 0.15. Find the probability she wins exactly 1 contest. Assume the events are independent. So there's that phrase they're telling us. So one contest outcome has no effect on the other contest outcome, right? So they're not conditional at all. They're independent events, which means I don't have to set up a tree. I don't have to set up any type of formula. It's just multiply when I use the and statement, add when I use the or statement. So I'm looking for the probability that she wins 1. Now, did it say which contest she wins? No, it didn't say which one she won. It just says she only wins 1. And so she can either win the first contest, lose the second, or lose the first and win the second. All right, so setting this up, she wins exactly 1, so she could win the first and lose the second, or lose the first and win the second. Alright, and so when we use the word and, you multiply, and we can multiply because they're independent events. We use the word or, these are 2 separate events, we add, right? I have one of those outcomes or the other. And so probability she wins the first times the probability she loses the second, or we add the probability she loses the first times the probability she wins the second, right? And we can do this because they're independent events. We multiply the and statement because they're independent events. And it's the or because I can have one event or the other. Alright, then I just have to plug in my numbers. So the probability she wins the first event is 0.1. The probability she loses the second event. So the second event's probability of winning is 0.15. So this is the complement to that event, right? So I take 1 minus 0.15, so that means she's got a 0.85, so 85% chance of losing the second event. So that's the chance of losing the second contest. Or, so we add, she loses the first, which again is the complement to the first. So the probability of winning the first is 0.1. So the complement of that would be 0.9. So she has a 0.1 probability of winning the first. She has a 0.9 probability of losing it. And then the probability of winning the second. So we multiply times that 0.15. Right? And then just make sure you're careful. Multiply and add correctly. Follow order of operations. So I just put this all in my calculator at one go. So multiply and add. So the probability she wins exactly 1 contest, 0.22. So she has about a 22% chance of winning one of them. We don't know which one, but she has a probability of 22% of winning one or the other, the first or the second. Which means if she only is winning one, she's losing the other. She also has a 22% chance of losing one, losing exactly one. Alright, next example. Which I believe this is the last one. Suppose that you have 2 startup companies. You have Company A and Company B. After collecting data on the individual companies, we've estimated that Company A has a 64% chance of making a profit this year, and Company B has only a 30% chance of making a profit this year. Assume the probabilities of making a profit for individual companies are independent. Alright, so there's our independent phrase. What's the probability that at most... Alright, so I've kind of hit one of each case, right? I've done an exactly, an at least, and now an at most. Alright, so we had an exactly in the last example. We had at least in the previous example, and now we're going to do it at most. So probability, we get at most 1 with a profit. And there's actually 2 ways you can do this. You can use the complement, or you could set it up. And I actually think the easier way is to use the complement. So I'm actually going to use the complement. Alright, the complement of this is 1 minus the probability we don't want. Well, at least one of them has a profit, meaning one of them makes a profit. Either A makes a profit or B makes a profit. Or neither of them make a profit. A is not profitable and B is not profitable. The opposite of that is both of them are making a profit. Alright, so I want the probability 1 minus the case where both A is making a profit and B is making. So I'm going to subtract the case when company A has a profit and company B has a profit. All right, we want to throw out the case where both of them are making profits, right? We don't want that case. We want all of the cases where at most one of them's making a profit. All right, so this is the case we don't want, so we're throwing it away. All right, so 1 minus that probability, so it's the probability A is making a profit times the probability B is making a profit because they're independent. So the probability of A was profitable was 0.64, right? 64% chance, so that probability is 0.64. And the probability B is profitable is 30%, or 0.3. Right, so make sure you're careful here. It's 1 minus this product. So make sure you follow order operations. Rule of thumb would be just put parentheses around that multiplication. Right, so 1 minus that is 1 minus 0.64 times 0.3. Actually, I'm just going to type it all in my calculator at once. So 0.808. And they're asking for probability. So 0.808 is the answer. So almost an 81% chance for these two particular numbers based on their numbers that at most one of them will make profit. So that's using the complement. I will kind of set it up. So a lot of times students will do it not using the complement. So I'm going to kind of set it up not using the complement just so you can see the difference. So this would be, if you want to, if you're curious. If you don't, then this video basically is done and you can just finish it up there. But I'm going to show you the way if you were just going to set it up without using the complement. Right? So at most one of them, so that means one makes a profit, only one, or none, or no profit. And so the hard part about this one, if you were going to set this up without the complement, is one of them's making a profit. So there are 3 cases. There's A makes a profit, and B has no profit. Or A has no profit, and B does. Or A has no profit, and B has no profit. So this would be, if you didn't use the complement, you have to have those 3 cases, and you'd add and multiply accordingly. And so A has a profit was 0.64 times B with no profit, which would be 0.7, plus the outcome A has no profit, which would be 0.36, times B has a profit, which would be 0.3, and then add the last case. Neither one of them have a profit, which would be 0.36. A is not profitable, and B is not profitable. If you multiply and add that correctly, it'll come to the same answer we got before. All right, 0.808. All right, so either way is fine. Again, the complement's the easier way to go, but sometimes students, for whatever reason, this particular problem, students don't necessarily use the complement. They use this method, and then they forget that there are 2 cases where one of them's profitable. All right, so a lot of times they'll leave off one of these 2 cases. So make sure you're careful. Either way is fine. Just make sure you understand the problem and answer it correctly. The last one's to be done on your own. Again, they are independent events, so find the probability she makes at least one of them. So this is the at least case. So try this on your own. I will post the answer to this later on, but this is just like the at least case we had in the basketball example. All right, so set it up, practice it. Again, I would probably use my complement on this one as well. Maybe 1 minus the probability you don't win either game. Alright, we will stop there. We finally finished 7.5, so after 10 videos and 13 pages of notes, we are completely through 7.5, but we do have one more section left to go, 7.6. But 7.6 isn't too bad if you understand trees. It's going to be more fun with trees, alright, and so we'll do that in the next video.